Yes, from Dublin.
Thank you, Mr. Chairman, and so thank you for the invitation. So, well, it's going to be quite different from the previous talk, but actually I will find some links with the previous talk. So, well, in order to save some time, I will move on. So, well, essentially, I work in 3 areas in wave research. Tsunamis, so it was mentioned in the previous talk, and I will not talk about tsunamis today. Then freak waves, so that will be about 2/3 of the talk today. And here are 2 illustrations of freak waves, and I will come back to these, so I'm not commenting now. And then wave energy conversion, and actually this is the reason why I'm in Ireland, to work together with Aquamarine Power, the company that designed this device, which is called the oyster, because it closes up like an oyster, if you wish. And this is the device in the sea. Now, the research on freak waves that I will present today actually is a joint collaboration with physicists in optics. So I want to mention these collaborators, John Dudley from the Université de Franche-Comté in Besançon, Gary Ganti in Finland, Neil Akhmediev in Australia, and Bertrand Kibler and Christophe Finot in Dijon in France. So, I will begin with some easy slides to introduce freak waves. And so rogue waves are large oceanic surface waves that represent statistically rare wave height outliers. So we'll come back to this in a second. Now, what are we talking about when we talk about the wave height? So I like this old illustration here. So it's the distance from the crest to the trough. And so let me first comment on this famous example of a freak wave. So that was in February 1986 near the coast of South Carolina. And it was a nice day with light breezes and no significant sea. Only the long swell, about 5 meters high and 200 to 300 meters long. So here's the captain talking. We were on the wing of the bridge with a height of I of 17 meters, and this wave broke over our heads. So this shot was taken while the ship was diving down off the face of the second of a set of 3 waves. And just to indicate the power of this wave, the foremast here was bent back about 20 degrees. So the reason why we study freak waves, essentially, it's because, they can do some damage, and also there can be some fatalities when the wave height is outside the design criteria.
Frederick, what's the horizontal scale of these waves?
Next slide, or it's coming in a few slides. Second example, that was last year. It was a cruise ship, the Louis Majesty. And so I was in touch with one of the passengers of this ship here, Mr. Daniel Connell. And so here's his description. The sea conditions before the large wave struck were fairly severe. The wave crests were in the 6 to 8 meter range. Of course, that's an indication from the other passenger. I don't have more details on this. There was only one, well, he calls it a monster Welle, using the German. The captain called it a freak wave. The ship was heeling over pretty severely. Walking required holding onto something. So it's a different situation. It was a rough sea here. The deck that was hit, it's deck number 5. And actually here you see the furniture and so on taken from the inside. And all these windows broke. The water came in. and actually 2 people died during that event. So the wave hit the port side of the ship. If the wave was 8 meters and the ship was heeling over at a 15 to 20 degree angle, that would bring the wave up to deck number 5. So what's the definition of rogue wave? Well, there is no definition. So there is one which is commonly used, which is this one, which says that a wave will be a rogue wave if it's the wave height is more than twice the significant wave height, which is the average wave height of the 1/3 largest waves. So actually it doesn't work for the previous case, for the cruise ship. This is less than 2 in that particular case. But, as I said, there is no good definition of freak wave. Now, to come back to Alan's comment, rogue waves are localized in space, so of the order of 1 kilometer square region, and in time, order of 1 minute. So here, what I always explain is, you are on a boat, and you have some friends who are 5 kilometers away from you. You experience a rogue wave, most likely they won't see any rogue wave. Or, said differently, then they go where you are, but 5 minutes later, they will not see the rogue wave that you saw.
They're much longer horizontally than they are their wavelength, right?
Well,
the wavelength tends to be about 100 meters, maybe.
Yes, okay, so then you are talking about the envelope in some sense of the...
No, I'm not talking about the envelope. I'm talking about along the crest.
Oh, sorry, on the transverse direction. Yes, and actually people describe it as a wall of water. So actually you will see that in one numerical simulation. I mean, this effect, I don't have a quantification of this transverse size, but yes, it's a, well, again, it's well, I cannot quantify it, but yeah, it's the descriptions are like it's a wall of water coming. You want to know all the answers at the beginning. It's so, well, as it says here, the second of a set of 3 waves. So in that particular case, there were 3 extreme waves, and it looks like it's often the case. People have often quoted the number 3, which is actually a bad news because usually they can survive the first one, but then some water comes in, and then it shuts down the electricity on board, and then the boat cannot be maneuvered, and so it becomes bad. Well, here in that particular example, the famous oil platform in the North Sea, the Draupner oil platform, and this is a recording on January 1st, 1995. And so here it satisfies the definition. The wave height was about, well, we go from 5 to -5, so about 10 meters, and then suddenly this big one, so from 18 to -7, so 25 divided by 10, that's more than 2. And also you cannot read probably, so this is the time in seconds, and this is 0 to 600 seconds. So quite localized in time. And then this is, I mentioned it, the elevation in meters, and this is from -10 here to 20. Now, how are these waves generated? So there are several possible mechanisms. Some can be explained using linear tools, and some require nonlinear effects. So among the linear effects, we have the focusing due to the continental shelf topography. There is directional focusing of wave trains, and I will say a few words about this one. So it's waves coming from different directions and in some way piling up at a particular point in space. Then the dispersive focusing of wave trains, it's based on the idea that water waves are dispersive, so the long waves go faster than the short waves. And actually this is what is used in tanks to generate some extreme waves. It's this principle, so you send some short waves first and then some longer waves, and then you manage to have all of them arrive at the same, together at a particular location. And then, this is also a well-known example, if you have waves and an opposite current, in some sense it kind of blocks the wave and makes it increase in amplitude. And so, for example, this is well known in the south coast of Africa. Now, the nonlinear effects, and this will be the emphasis of the talk today. So, water waves are unstable. So you can have an exponential amplification of, noise, for example, so instabilities. And then once this instability develops, you can have the formation of quasi-localized surface states. Now, we had a discussion with Alan Newell, and he likes the blackboard to explain things. There is one, it's always difficult to explain the fact that water waves are dispersive to a non-expert audience. And here, PowerPoint helps to illustrate this. So I like this animation here. This is just the superposition of 3 monochromatic waves. And so here, it's a distance of 2 kilometers. And here, you have 22 waves. Here, 25. Here, 29. This one is 1 meter. This one, 2. And that one, 1. And this is simply the superposition, linear superposition of the 3. And so you get these wave packets, which is the way that waves travel in the ocean. And then, of course, then it clearly shows the 2 velocities, phase velocity, that's following the red dot, and then the group velocity, that's following the green dots, and in deep water, then the group velocity is exactly half the phase velocity. So why am I showing this? Well, do we actually observe this in the ocean? And now there are some very nice observations of swell propagation from satellite data. So these data were provided by Ifremer and Boost Technology in Brest. And so typically there is a storm which is being formed, for example, south of near New Zealand. And then some waves are going to propagate across the Pacific Ocean. And the color code is simply the wave height here. And what you see is that these wave trains travel in different directions. So it could well happen that we have this directional focusing in the ocean based on this type of illustrations. And actually these dots here propagate, of course, with the group velocity. So if you know the period, you can compute this group velocity. So you can predict relatively accurately when these waves will arrive in California, for example, and when you will have some very good waves for surfing. If you go to surf websites, actually sometimes they indicate, there will be some very good waves 3 weeks from now, and that's based on some storms that were generated over there. So that's ocean observation. Now I want to show 2 other types of... So first of all, now in a wave tank, this is some experiments performed in Nantes, which has the nicest wave tank in France. So École Centrale de Nantes, that's a snake wave maker with about 30 panels. And so you can program the motion of these panels here so that you will concentrate the energy at a particular point inside the wave tank. So here it comes. A big wave is starting to form at a given location inside the wave tank. So here it is. And it's quite spectacular. It's not so easy to do. I mean, it requires some expertise as an experimentalist to find this type of focused waves. Okay, so that was we saw the ocean, we saw the lab. So now we'll show the numerical simulations. So I don't know if it's going to load. It's a big file here. We'll give it a few seconds. Yeah. Okay. So these are now numerical simulations that we performed a few years ago with our three-dimensional numerical wave tank, which solves the fully nonlinear potential flow equations with a free surface. And here, so we have the wave maker in the numerical wave tank, and so this extreme wave is starting to form in the middle of the tank, and now with the computer graphics, we'll start to move closer to the wave and look at it ahead of us. So there is this kind of a wall of water forming and coming towards us. So, well, these types of computations are, not so easy. I mean, it requires some computing time. And of course, this is potential flow. So once the wave starts to overturn, then we stop the computations. Okay, so now we talked about the nonlinear Schrödinger equations, about some of its drawbacks yesterday. But here for today, I'm quite happy with the nonlinear Schrödinger equations. So what do we have in the nonlinear Schrödinger equation? What does it contain? And actually, this is taken from Osborne's book that just came out recently. I will put a picture of the book later. So with the nonlinear Schrödinger equation, we have the superposition of weakly nonlinear Fourier components. We have the Stokes wave nonlinearity, and we have the modulational instability. And Al Osborne distinguishes two types of nonlinear waves. Population number one, that's a weakly nonlinear superposition of sine waves of this type together with the Stokes waves correction. So it's essentially 1 and 2. And then the second population is item 3, which predicts the existence of unstable wave packets, which can rise up to more than twice the significant wave height and then create a rogue wave. So unstable packets are a type of nonlinear Fourier components. In the NLS spectral theory, the spectral contribution arises from the Benjamin field stability and obeys a threshold effect. Only large enough wave fields have unstable modes in the spectrum. So here's a picture which contains quite a bit to summarize the Benjamin field stability. So first of all, this diagram here, that's the spectrum here, and that's the frequency f here, and we have the frequency of the carrier in some sense, the leading frequency here, f0. Then this is the classical illustration of the Benjamin field stability that we have, for example, in the nonlinear Schrödinger equation. So these two lobe here, and so it goes all the way to f0 plus IBF delta f. So delta f is the modulation, and IBF is this index, the Benjamin Fair parameter. So here it's written the space-like Benjamin Fair parameter. So it involves the carrier wave steepness divided by the spectral bandwidth. So this is with the delta k, and this is the same, but now with the delta f. Now, here we have the jump swap spectrum here. So these two lines here indicate the unstable band of the spectrum, and that's the steepness written in terms of the significant wave height and the frequency f0. So if one wants more rogue waves in an experiment, one needs to increase the significant wave height and increase the number of carrier oscillations under the modulation. That is, make the spectrum narrower. Incidentally, this parameter was first introduced by Tracy in 1984.
Just to clarify, so this is now a completely different take on the problem, right? This is a one-dimensional
It's a 1D, yes, here. Oh, yeah, oh, sorry. My mistake. It's, so when I said that I would talk about two effects, the directional focusing, that was what I showed in this, the ocean, wave tank, numerical experiments, and then I switched, without telling you, to the nonlinear effects. And now I'm concentrating on a 1D. But it's, well, of course, here, after the wave concentrates at a particular location, it becomes nonlinear. But the mechanism at the beginning is a linear focusing.
How do you know what you saw in the ocean is due to...
Oh, I don't know. This is a conjecture. It's like, so it's my colleagues at Ifremer who thinks that, there is the directional focusing in the ocean. But, there is no quantification yet of that. Okay. So, now the modulational instability. So the classical type of experiment, and actually both in the tank or numerically, that's the so-called Benjamin Fair instability. So you have an initial wave condition, which is a monochromatic deep-water wave with a small disturbance added. And after several wave periods, the instabilities develop and energy becomes concentrated at a single peak in the wave group. So two ways to look at it. This is the initial wave shape. This is at 57 periods, 58, and so on. And so you see the deformation of the initial wave. And then actually there is a recurrence, so it's going to disappear, and the wave will almost go back to what it was. And then here it's snapshots of the surface elevation during 10 wave periods. So this is time and distance. And, of course, this is Brooke-Benjamin. So the Benjamin Fair instability actually was studied by several people essentially at the same time. So here it's just to indicate at least, 4 groups who looked at this type of instability in the late 60s, and there is also Dave Benny and, Alan too. With Dave Benny, you have a paper in the late 60s on this. So now I'm going back to more details about this Benjamin Fair instability. Here, because I will talk about optics, it's in the time nonlinear Schrödinger equation. So actually this is space and this is time. Or also it's the nonlinear Schrödinger equation that we use when we have a wave maker situation. But it doesn't matter for the explanations. So we have the exponential growth of a periodic perturbation. So here we take this solution to the nonlinear Schrödinger equation, and then we perturb it with the epsilon here, which is given here. So it's I kappa xi minus omega tau. And then you do the linear stability analysis of this solution, and then you find the value for kappa as a function of omega. And then the growth rate is simply twice the imaginary part of kappa, and it's given by this. So that's, again, it's this lobe here that I show again. And so forget about A and B. They will appear on the next slide. So here we have omega, and we have instability when omega is between 0 and 2. Then this is imaginary. And then, of course, there is growth. And so this is the growth corresponding to the given omega.
But you have to say that this growth is actually fairly slow compared to the period of the wave, okay? Right?
Yes.
And a freak wave erupts just like, boom, like this, right?
Yeah, wait a second, Alan. Yeah. So actually, the emphasis has been people who have tried to study the Benjamin Fair instability have concentrated on this point here, Why? Because this is the one that gives the maximum growth in terms of the instability. We are going to concentrate here. Now, you might say this is not a good point because then the growth is almost nothing. But we'll explain why. We looked at this area. Okay, so there is the Benjamin-Serre instability. So the instability develops. That's a linear stability analysis. What happens to the solution? Well, it turns out that there is some type of nonlinear continuation of this instability, and it's provided by these solutions, the breather solutions to the nonlinear Schrödinger equation. So it's the same equation here, and this is an exact solution to the nonlinear Schrödinger equation, breather type solution. So this one is usually referred to as the Archimedes breather in the literature. And now, these are these coefficients A and B. So A is related to omega by this formula, and B also, that's the connection with omega. So when omega goes from 0 to 2, A goes from 1/2 to 0, and then B here varies between, it essentially follows this curve. Okay, so what these solutions look like, here is an example of this breather. So why is it called a breather? Because it breathes. So in that solution, there are some cosine omega tau, and then some cosh and sinh of the xi variables. So what happens as A varies? Well, okay, we said that A was between 0 and 1/2. A equals 1/4 corresponds to the maximum growth. And this is this solution here. But actually, we can also compute this solution if A is larger than 1/2. Of course, it's going to change. And essentially, now the cos here, cosine are going to become cosh, and the cosh are going to become cosines and so on. But we can compute these solutions. And actually, these are the Kuznetsov or Ma solutions, which are also well known in the literature. So here we are trying to reconcile everybody, Akhmediev, Kuznetsov, Ma, by looking at all these solutions in a continuous way. Okay, but A equals 1/2 plays a singular role here. So what about the case A equals 1/2? So here, most of you will recognize Howell Peregrine. And actually, he has the solutions for A equals 1/2. It's the what we call the Peregrine-Soliton. It's a very condensed expression here. Again, exact solution to the nonlinear Schrödinger equations, algebraic. And so this solution here is the emergence from nowhere of a steep wave spike. So you see that this solution is, well, in between these two, the limit as this will go to 1/2 this way, and here to 1/2 the other way, and it's going to give a single spike. So it's really localized solutions both in space and in time. So now also it's important to realize that, this is a soliton like the other solutions actually. On a finite background, at infinity this psi goes to 1. So that's important to remember. And then this solution is actually the one that gives the maximum contrast between the peak and the background amplitude. And actually, for this particular case, it's easy to see it gives 3. So the ratio is 3. So it's, well, in terms of freak waves, it's above the 2 threshold. But, as I said, we are here now, in this plane here. So there is a 0 gain. So actually, this type of instability will take a long time to develop. So can we observe this solution? So here is a quote from Lighthill. as Sir Cyril Inshall would have observed, fluid dynamicists were divided into hydraulic engineers who observed things that could not be explained, and mathematicians who explained things that could not be observed. So can we observe this? As I told you, I started to, some physicists in optics contacted me and to work together on rogue waves, because some years ago, people also found rogue waves in optics. Now, I'm not going into the details. In optics, you also have the nonlinear Schrödinger equations. You have dispersion. You have nonlinearity. So you can expect you have the modulation instability, so you can expect some of the same phenomena to occur. And so this is what we did. So we had, several research areas on freak waves together with people in optics. But then at some point, initially the point was that with optics we would understand ocean waves better. But then it turns out that the ocean waves are much richer than optics in some sense. And I said, we have much more in ocean waves that you have in optics, so maybe you could discover some new things in optics. So it went the other way around, like we learned more in optics than in ocean waves, although you will see that we are getting there. So then we decided that they would try, my colleagues, to find this soliton, this peregrine soliton, experimentally in optics. And of course, experiments in optics are easier to perform. The laser is maybe the size of these two tables, so it's much easier to perform than water wave experiments. And to make a long story short, this is so there are three data here. The blue circles are the experiments of this peregrine soliton. The line here is the analytical expression of peregrine, and these are simulations on the nonlinear Schrödinger equations. Almost. It's in optics, it's actually slightly more complicated. It's a generalized nonlinear Schrödinger equation, but I won't go into these details. So pretty good agreement, and so actually it provided my first paper in Nature together with people in physics. So I think it helps to be with people in physics. It's almost impossible to have a paper in Nature in hydrodynamics, but I think it's easier in physics. Anyway, so I can show a video of this solution. There is nothing really.
Was it difficult to prepare?
Difficult to prepare. Yeah.
Kind of get it exactly right.
Yes. Yes and no. It's.
I mean, for instance, in usual fibers, the attenuation is very strong. How did you
All the details are in.
You boosted.
A little bit. Yeah. So here's just the numerical simulation of this solution with this emergence of this peak, and then the dots are the analytical. Okay, so then, and of course, we did that in optics because, at the time we didn't think that, we could get it in hydrodynamics. And, just 2 weeks ago, there was a paper in Physical Review Letters by some experimentalists in Germany, in Hamburg, and they managed to get the same solution in a wave tank. So the idea was, and actually their paper says that they tried to put for the wave maker the motion essentially provided by the peregrine soliton. So it's like trying to get what you have as an input, but it does not always work. But in that particular case, it worked. So here's that's the distance from the wave maker. That's the time in seconds. So that's from 0 to 70 seconds. That's 0.1 meter to 9 meter from the wave maker. And so essentially you see the signal that they put inside the wave tank, and then it propagates, and then this spike develops. And this is another a blow-up towards the comparison between the analytical solution and the experimental results, so a pretty good agreement. Now, the only thing that you probably haven't seen yet is what is the size of this wave. It's here, and it's 2 centimeters. So it's a 4 centimeter freak wave, or 6 centimeter freak wave here. So the background is 2 centimeters, and then the spike is roughly 6 centimeters.
How quickly did it arise? Look at it
Well,
slowly.
you see, at this particular point, it's at 40 seconds, so it's...
So in terms of the wave theory?
They don't, they actually didn't, which is a pity, they didn't put all these simple calculations, and I didn't have time yet to
You can see in the picture, it's more than 10 oscillations per
Yeah. So, now one thing that I haven't said is, so actually where is this energy coming from? Well, essentially, it's pumping energy from this background state. That's the way it works for this solution. Okay. So I will skip this. And as I said, so here are 3 recent publications on rogue waves. So there's the book by Christian Carif, Efim Pelinovsky, and Slunayev, Rogue Waves in the Ocean. Then this book by Al Osborne, Nonlinear Ocean Waves and the Inverse Scattering Transform. And then a special topics issue of the European Physical Journal on rogue waves, discussion and debate. Okay, what I want to do in the last, maybe 10, 15 minutes is, 10 minutes, is to change topic now and to, we've talked about wave energy in a negative way with tsunamis, with freak waves. So now let's talk about wave energy in a more positive way, and let's say a few words about wave energy conversion. So this project I'm working on is together with Aquamarine Power, which is a company that has developed the Oyster device. And actually this picture shows the Oyster device in the Orkneys Island. And so we have a collaboration right now. Actually, it's quite interesting. So this is Google Earth. And actually, it disappeared with a change of resolution. So let's see if I can... Yeah, okay. So you actually see the... maybe you don't see it from where you sit, but there is the green arrow. So actually, if you go to Google Earth, and here's the location here, you see the Oyster device, the first prototype, in the water. So what's the technology? It's quite simple in terms of design. There is this large mechanical flap which moves back and forth with the motion of the waves. Then 2 hydraulic pistons pump high pressure water via pipeline to the shore. And then there is a conventional hydroelectric generator located onshore. It's typically in water depths of, let's say, 10 to 12 meters, and then located near shore, typically 500 to 800 meters from the shoreline. So I will show quickly 2 videos. So that's, to show the device in the ocean. So, while there is the video, so I will start talking about the various difficulties that even though the design is simple from an engineering point of view, of course there are some problems, but From a fluid mechanics point of view, it's quite bad because first of all, it's intermediate water depth. It's definitely a three-dimensional object. Then it's neither a small structure or a large structure in terms of if you compare the width to the wavelengths. So no simplifications there. Then because of this type of motion, there is some vortex shedding on the sides. So, and then also we are starting to worry about the biofouling on the device. So very rich in terms of hydrodynamics. And here, I'm showing quickly this one, just to show the fact that, of course, these devices will work if they are put in farms where you will have an array of such devices. In this particular case, it will be a line array because of the water depth constraint. So now you will see the prototype number 2, which will be these 3 devices in an array. Now the location is not yet completely agreed upon.
So what pressure difference roughly can you get ready?
I don't know. I mean, I have the answer, but I can give it to you later. So
what happens to these guys if they get nuclear bombs?
well, okay, I haven't worked on the rogue wave. I have worked on the tsunami on this, and it's not very good, okay, because of the 10-meter depth. And so actually I was on March 11th, I was in Belfast looking at the experiments when the tsunami occurred. So the first question they asked, can you tell us, if, because they want to install these devices in Oregon, for example, where there could be tsunamis. So they immediately asked what would be the effect of a tsunami on this. But so,
Not very much. Not very much.
well,
Because most of the tsunamis that will hit the Oregon coast will actually be their crests will be perpendicular to the coast. I mean, you can see that from the recent ones. So these things are the opposite direction.
yeah, but the thing is, the plan is, if there is a tsunami, the device will be shut down anyway. So it will be lying on the seafloor. But, a tsunami, even if the device is, it has some thickness, it has some width. So, well, 500 meters from the coast, it's, we've done some preliminary computations, but I will not talk about this. So the project is as follows. So the first prototype is the one you saw in the picture. That's Oyster 1, so 315 kilowatt demonstrator. It was installed in October 2009, and actually it has just been decommissioned. The Oyster 2 project, so there will be 3 devices of 800 kilowatt each. You saw the picture. And the first one will be put in the water before the end of the year. And then, of course, Oyster 3 project later. So in Ireland, the first project for a wave farm is scheduled for 2015. And since, there is no consensus yet on the technology, there will be a farm involving 4 devices. This is Pelamis, and this is Oyster. So the consortium includes 4 of the leading technology developers, and it will be installed, of course, on the west coast of Ireland. So what are we looking at? The wave impact and pressure loads on a single device, the optimal device spacing for an array, the preferred geographical locations for nearshore sites in Ireland, and then also the biofouling issue, so the biological growth on surfaces in contact with water. The experiments right now are being performed at Queen's University in Belfast. So this is model here in the wave tank, and actually we'll do some experiment next week. Now, one thing that also we are looking at is the scale effects, because here, usually, of course, you use fruit scaling for this type of experiments, but we are concerned also with the Reynolds scaling, and of course, you know that we cannot get both, because essentially we cannot change the viscosity of the liquid. So just to realize that the Reynolds number is much larger at full scale than at small scale. For example, at scale 1/40, the viscous forces on the model are multiplied by a factor 253 if only fruit scaling is satisfied. So we have to understand this bias better, and this will be done with numerics. So I will just show quickly some preliminary results by Emiliano Renzi, one of my postdocs. And now this is the analytical theory for a very simplified oyster 2D. There is the hinge, and then the 1 degree of freedom here for the rotation of the device, potential flow theory, and linearized equations. And so the wave train is incident upon a moving structure. And so we have scattered waves and radiated waves. And the equation of motion of the device has, we take into account the moment of inertia. Of course, we are extracting energy from this, so there is the rate of power of takeoff, the buoyancy of the device, and then the hydrodynamic pressure. And so then if we use this type of ansatz, then we get this equation here. So these are some results from the 2D linear theory for the added inertia versus period, the radiation damping versus period, and the stroke to wave height ratio as a function of kh. So oyster is most effective for long waves in shallow water, so typical values of kh of 1, roughly.
Is that just because the water moves throughout the whole depth, right?
Yeah, that's the main effect. Now, there were some students at Queen's who did some numerical modeling with WAMIT. So it's the linearized water waves equations, but it's 3D. And so here's a comparison between the linear theory 2D and the 3D numerical model. And so for small periods, there is a similar behavior between the two. But then for the large periods, the matching is not as good. And so for long waves, the 3D effect cannot be neglected. And so, briefly speaking, then, if you have short waves, short transverse waves, essentially they will cancel out. But then if you have long transverse waves, and this is the width of the device, then you won't have this cancellation. So now this is the connection with some work by Chang Mei on the Venice gates. Actually, it's quite remarkable that these gates have similar types of dimensions. Now, of course, the gates are supposed to be next to each other, but there was some interesting work by Chang Mei and his collaborators, and what they found is that some trapped transverse waves near a barrier of rolling gates can enhance the stroke, which actually for Venice was not good, but maybe it's good for us. I don't know. So, just want to conclude with some, good and bad news. So oyster might be a simple device from the engineering point of view, but it's really challenging from the fluid mechanics and numerical simulations point of view. So I'm listing here 1, 2, 3, 4, 5, 6, 7 effects that we have to deal with. And honestly, I don't know how we'll do that, but that's part of the challenge. So what are the difficulties? First of all, it operates at intermediate water depth, and this is the least understood part of water waves. So we know about shallow water, we know about deep water, but not as much about intermediate water depth. Obviously, it's a 3D problem. Then it's neither laminar flow nor potential flow. So the Reynolds number is of the order of several thousand, and there will be some vortex shedding. So we have to take this into account. We have, of course, a moving solid boundary, which has a relatively large motion. We have a free surface. We have an intermediate size structure. So it's not a small structure compared to the wavelength. It's not a large structure compared to the wavelengths. It's in between again. Of course, we expect the waves to be nonlinear. And then we'll have to deal with the coupling with the biological growth. So again, the device was in the water for 2 years almost, and there is quite a bit of growth. Not only, on the device itself, but, it could develop some laminars and so on. So then again, that's a connection with the previous talk. We'll have to deal with these laminars attached to the device, and will they affect the motion of the device? So, quite a bit of work in the coming years, but that's really exciting. Thank you.
Question?